Excited to be here today to talk to you about our first detections and confirmations of Gaia astrometric exoplanet candidates. They're called Gaia 4 and Gaia 5, which we published in a paper that came out just earlier this morning. So let's dive in. So Gaia has revolutionized multiple areas of astrophysics that has come up in multiple talks throughout the conference today and yesterday. And in its astrometric monitoring of then billions of stars in the Milky Way, it is now then poised to deliver on its promise to detect hundreds, if not thousands, of planets with the astrometric technique. And the astrometric technique then relies on measuring the gravitational wobble of a star due to an orbiting companion. And then the goal is then to resolve the Keplerian orbit, which I'm showing over there, on top of the effects of parallax and proper motion, which then appears as these spirals as seen on the plane of the sky. And the virtue of the astrometric technique is that by resolving the orbit, it's sensitive to virtually all of the orbital parameters of a planetary system, including the inclination of the orbit, and gives us the opportunity to get a true mass estimate of the planetary companion. This is then very, very complementary to many different exoplanet detection techniques, including the radial velocity technique, the direct imaging technique, and then in some cases, the transit technique. And as I mentioned, Gaia is now really poised to detect multiple planets, hundreds if not thousands of planets at these intermediate orbital periods, giving us further insight into the population and occurrence rates of planets at distant orbits. And as part of Gaia DR3, which came out just a couple of years ago, that released then astrometric solutions for the first time. This included tables of hundreds of thousands of binary stars. And here I'm showing then the sample of the ones that are at the lowest then masses, suggesting that they're then a collection of substellar companions, visualizing here the sample around the M stars on the left and more massive stars on the right. Most of these have then masses that are compatible with brown dwarfs, but if we take a look over here on the very tail here at the distribution, some of these are then consistent with being planetary. And in this context, 72 of these were listed as Gaia astrometric exoplanet candidates, which are then the prime candidates to look for planets. But as we were very familiar with when using the radial velocity technique and the transit techniques, these candidates remain candidates until we have confirmed that these are indeed true planets and ruled out then false positive scenarios. So let's take a look at the main false positive scenario in the case of an astrometric candidate. So here I'm showing what we actually want. A dark planet companion orbiting around the star. And the star is orbiting around the common center of mass with the same major axis of A1 over here. Planet has the same major axis of A2. And because the planet is dark, the photocenter orbit, which is the actual orbit that Gaia is measuring, is the same orbit as the orbit of the star. However, if we have a close to equal mass and equal flux binary, that means that the center of light is going to be in between the stars, the two stars, and then can masquerade as a planetary system. So here it's essential to know the host star to confirm that we have indeed a dark planet companion and rule out the case on the right. So this is exactly what we have been doing. Then following up these Gaia astrometric exoplanet candidates with precise radial velocity facilities, including these that I'm showing over here, including the Habitable Zone Planet Finder on the 10-meter Hobby-Ebbeli telescope, the NUIT spectrograph on the WIN 3.5-meter telescope, FIES on the NOT telescope, and recently we've expanded our efforts to include spectrographs in the south. In the purposes of this talk and for the paper that we just published, I'll be focusing on the observations from the northern instruments. So what do the properties of the astrometric candidates look like? Here I'm showing where they land on a Gaia color magnitude diagram, landing then on more or less on the main sequence with a few exceptions. As we started and as part of DR3, some of these systems actually were known exoplanets, which I'm highlighting here in green. These are the systems that were already known exoplanets and had been characterized before, and then Gaia detected astrometric variations there. A couple of these systems, which I'm showing in red, were quickly identified as binaries, and then 3 of them, which I'm highlighting with a black X, were eventually withdrawn due to issues in the astrometric solutions. However, there is a big sample here of M and K stars primarily, which we have been focusing our attention on because they need a follow-up observation, so we're extremely excited. Okay, are these planets or are these false positives? So now I want to walk you through an example target that we observed, Gaia ASOI 41. Here I'm showing the Browning function from HPF as a function of then the velocity. The Browning function is a very close cousin to the cross-correlation function, so you can effectively think of them as more or less equivalent. Gaia ASOI 41 is a few Jupiter mass expected companion with a period of around 480 days around a mid-M star. So what does the Browning function do as we continue to get additional spectra as a function of time? Let's take a look. Unfortunately, it starts to split out into 2 lines, and it is indeed clearly a spectroscopic binary. What we also see here is that the peaks are more or less the same height, which means that we have indeed the similar scenario that I was talking to before, almost equal mass binaries. So in our paper that we just published, we've then done this for all of the northern M and K star Gaia ASOIs, and out of those 28, 21 of them are false positives. I'm highlighting those here with the red squares. The upshot is that the remaining 7 are still compatible with the dark companion case, and then could be then prime candidates for substellar companions. And 2 of those 7, which I'm highlighting here with the green stars, we have fully confirmed now. And then I'm really excited to talk to you about those in a bit more detail. Those are called Gaia 4 and Gaia 5, which I'm highlighting over here, visualizing the orbits as Gaia sees them on the plane of the sky from the Gaia astrometry. Gaia 4b is then a 12 Jupiter mass planet in a 570-day orbit around a early M, late K star. And Gaia 5b on the right is a 20 Jupiter mass brown dwarf in a 360-day orbit around a mid M star. And Gaia 4 is then the first confirmed astrometric planet from Gaia, in the sense that Gaia fully detected the orbit, solved the parameters, and then we have confirmed it with a spectroscopy. So we're tremendously excited about that. Press releases just went out earlier this morning, so it was a very fun morning, an early morning, where ESA has press releases out on videos, so if you're curious, definitely take a look. I wanted also to show you and highlight some of the data that we then obtained on the targets, because from the Gaia astrometry, we can calculate what the expected radial velocity then curve is. And here I'm showing the 1 sigma region. And what are the radial velocities that we obtained, just purely overplotting them on top for consistency checks. Nicely follows the expected orbit. And then this opens up then the opportunity to jointly model the astrometric solution with the radial velocities, which I'm doing over here. Then nicely collapses the radial velocity curve on the right, and then I'm showing then the astrometric orbit in the Ariane deck space, showing the Gaia-only orbits, random draws from that in black, and then the jointly modeled then orbit in purple. But then you might ask, so how are we actually doing this modeling? Because the Gaia astrometric underlying time series are not available yet. So in this case, we are doing an intermediate step where we build a log likelihood function that is just the sum of the log likelihood of the radial velocity, standard log likelihood, And then we are here tapping into the covariance matrices, sampling them that are available as part of the astrometric solutions. So in this case, where we have fully confirmed that the radial velocity then orbit agrees with the astrometric solution, then we are confident that this is accurately describing the system. Because there are some systems where the astrometric solution and the radial velocities are not agreeing, and then it's unclear what the reason is, and we have to wait for DR4 to really elucidate what is happening there. But for Gaia 4 and Gaia 5, the radial velocities and the astrometry agrees well. Similar plot for Gaia 5. Radial velocities agree extremely well. This then reveals a eccentric brown dwarf with an eccentricity of about 0.65. This is then where Gaia 5 and Gaia 4 look like in comparison to other massive companions around low mass stars. I'm very excited about these objects because these are, like Jesse and others mentioned, that these are relatively infrequently formed around low mass stars, and Gaia will be uniquely sensitive to these types of objects. One area over here is that there's currently a complete void of these Jupiters, sort of a Jupiter desert here around the lowest mass stars. And are they just not formed at all, or are they formed just in very few cases? And I believe Gaia will be one of the key then tools for us to find out. We can also take a look at the same plot in a mass ratio sense on the y-axis. Then this becomes more of a wedge. One thing that I'm very excited about then probing with Gaia, and as we find more of these systems, is this then void over here, or desert, then an observational relic of the fact that the planets tend to be formed from core accretion, and the brown dwarfs are being more formed from gravitational instability or molecular cloud collapse. And then we'll just briefly glance over this on my last slide. Gaia will also give us a lot of architectural information about the eccentricities of these systems, inclinations. Here I'm just showing the eccentricity distributions of planets and brown dwarfs around low mass stars, showing that there are some differences, especially we're seeing much fewer than brown dwarfs on circular orbits than planets. And Gaia will really help populate and gain further insight into this. So I'll then leave my summary slide up that we're starting to find now some of the first Gaia astrometric planets. And the future is really exciting, where DR4 is just right around the corner, where we're going to be expecting to find hundreds or thousands of planets. And there's going to be a lot of effort needed to characterize and follow those systems up. Happy to take any questions.
Well, questions in, I think up in the back. Oh. So we're here for the announcement of the first Gaia-only exoplanet detection, as opposed to Gaia plus Hipparcos. Okay.
Yeah, if you go back to the false positives, are there any other ways that you can follow up these false positives? Like, for instance, can you interferometrically resolve these close binaries?
So your question is, can we use other techniques than just the radial velocity technique? Yes. I mean, there have been some really cool recent papers with gravity following up some of the brown dwarfs, where you can actually then detect the brown dwarf. So that is one way.
Let's get Jesse with the last question here before we go to coffee.
Thank you. 75% is a really high false positive rate. Do you know if they'll do anything different in DR4 to bring that down? Like, is there any other tests you can use? Now that you know where the false positives are you working on improving identifying candidates, ASOIs in the future?
Yeah, I mean, it was also relatively high for us. We stayed away from sort of interpreting that too much in an astrophysical sense, because it was a bit unclear to us exactly what went into the decision matrix of which systems were decided to be listed as Gaia ASOIs versus not. But I think all of that will become a lot more clearer as we find more of these systems. But we're actually working on finding out if the other ones of those 5 continue to be then planets or false positives. So we're excited to find out.
Thank you. And for the person who asked, they're not in the archive yet. They came out this morning. I like that you think we're magic, but not that magic.
You're putting them in the archive right now. All right, let's give Goodwin a hand.